Welcome, we are Ignasi Ballarà and Francisco Herranz, and we will talk about the Alpha-MOS transistor model.
These are the main points we will cover. First, we will introduce a new equation for the drain current when using nanometer technology. Then, we will explain the physical phenomenon that these equation models and clearly establish the alpha power law. Afterwards, we will go through the technical aspects of this law, such as delay and power consumption, and end with some conclusions. Now, let's proceed with the introduction.
You are surely familiar with this equation. It shows how the drain current of the MOS transistor has a quadratic dependence on the gate source voltage. As you can see in the graph, though VGS increases 0.2 volts each time, the saturation current increases quadratically as mentioned before. Well, we are sorry, but we have to tell you that... It's a trap! Actually, when we are working with submicrometer channels, the 2 power is substituted by an empirical alpha, which is a new parameter that we now need to take into account since the short channel physics are considered. But why does this happen? Let's go take a look. Let's now explain why this modification is required.
When the transistor turns on, a channel is created between the drain and source terminals. Each carrier in the channel is accelerated to an average velocity v, which is proportional to the electric field E. Mu, the carrier mobility, is the proportionality constant between them. This electric field is inversely proportional to the distance of the channel, which means the distance between the drain and source terminals. Thus, as the terminals get closer, the electric field increases and so should the carrier velocity. Nevertheless, it is empirically demonstrated that there exists a critical electric field above which the velocity is no longer proportional to the electric field and reaches a saturation state. In order to model this behavior, mu is substituted by an effective mu, which is a function of VGS. In this plot, you can observe the evolution of the carrier velocity as a function of the electric field. It is clearly visible both the initial proportionality between velocity and electric field and the velocity saturation when a certain field is reached.
This behavior is modeled with different approximations, which depend on the critical field. Nevertheless, alpha power law provides a good enough approximation without depending on the critical field and restricting its use at the velocity saturation area.
Alpha power law provides an expression to capture the behavior of IDS when there is velocity saturation. Alpha is referred to as the velocity saturation index and varies between 1 and 2. When dealing with long channel transistors, alpha becomes 2 and the typical widely known expression is used. But the closer the terminals get, the closer alpha gets to 1. As it can be observed in the plot, some of the most immediate consequences of this model are the earlier saturation of the drain current and the lower output resistance. Now, let's consider some technical features of this new model.
All the contents mentioned before and the new physical phenomena that we are facing have implications relating the behavior of the transistor. First, we take into account the classical delay definition. This is the time difference between half VDD in the input and half VDD in the output, where VDD is of course the supply voltage. We must say that in overall, when alpha gets smaller, the delay increases. So delay and the alpha value are inversely proportional. There is a big advantage though. This big advantage of the Alpha-MOS is that the delay of this is much less sensitive to variations of the supply voltage tension. This phenomenon can be seen in this graph, where we see that as alpha decays, variations in the supply voltage have lower impact in the delay value. In this graph, though, we have to say that we consider that the supply voltage has a value of 3.3 volts, as we can see in the horizontal axis. Secondly, we also have to mention that the equivalent resistance of the Alpha-MOS transistor is proportional to the supply voltage to the power of 1 minus alpha, as we can see in this expression. At the same time, as we mentioned with VDD variations and delay, we can say that the same phenomenon happens when regarding the equivalent resistance. So, in other words, as alpha decreases, the resistance variations are smoother when faced with variations of the supply voltage.
Now, let's take a look at power consumption issues. First of all, we must define a concept, PS, the short circuit power per switching, which is the power consumed when a CMOS inverter is switching. In the graph, it can be seen how, As the velocity saturation index increases in the horizontal axis, the short circuit power factor decreases. The different curves just represent the power difference when the threshold voltage is bigger or smaller. We can see that, for example, when the threshold voltage represents a 10% of the power supply, the power is much higher than when it represents a 30% as expected. In the end, what is important is to understand that the short circuit power increases as the velocity saturation gets severer in short channel MOSFETs. And now let's summarize the most important issues.
First, when the distance between source and drain terminals is reduced to a certain point, the carrier velocity stops being directly proportional to the electric field. This reflects the need of a new model, the alpha power law.
Second, this model shows an alpha power dependence between IDS and VGS, different from the quadratic dependence seen until this point.
Third, in this new model, both equivalent resistance and propagation delay are less sensitive to supply voltage variations, which can be considered as an advantage.
And, regarding the power, it increases as the saturation gets severer.